Okay, takes 5 seconds to start. Good morning, ladies and gentlemen. You see that I have some new hardware here. We'll be doing technology demonstrations this morning. We'll also do another technology demonstration on Thursday. I know some of you have trouble registering your clickers. I'll get to that in a second. At least I'll hopefully give you a test drive of that process quickly. And then we'll actually try to see how they work. This week, if some of you have either don't have your clickers yet or haven't brought them today, that's okay. Anything we do today and on Thursday is pure technology demonstration or rather a test. Physics is experimental science. We are doing experiments here. And then once we have proven that technology works, next week it will actually be counting. So before I start, let me actually again pause here to see if you guys have any questions about physics. I'm happy to answer, and if not, we'll deal with logistics and then the material of today. Hopefully you guys have read some articles, have written essays this week. They will be graded later this week, and then you'll get feedback. So if you have any issues you would like to bring up related to what you have read, now would be a good time. No? Okay. Well, if you think of something, let me know. So in the meantime, let me walk you through a couple of logistical issues. So, okay, two things again. Homework was due, the essay part of the homework was due last night at 11 o'clock. A quiz part of this week's homework was due 12 minutes ago at 9:30. If you have looked, which I hope most of you have done that, at this week's quiz, there were 2 questions related to last week's material, energy, and 3 questions related to this week's material, chapter 2, heat. And so again, the point of this is to stimulate, to encourage you to read before you come to class, so that you actually come prepared, you come maybe slightly confused, but willing to get your questions answered and some of the issues clarified. So again, don't be shy about asking questions. If your question is about some material that I'm just about to cover, I'll defer it. Otherwise, I'm happy to answer it right there and then. Second part is, I know a lot of you have had trouble with these devices. These are these interactive clickers, which we'll use in about 5 minutes. So pull yours out. What you need to do, actually, in order for it to function today, nothing really needs to be done. When you turn yours on, if it's graphical like this is clicker 2. Yours probably is white, mine is blue because I'm special. It should say the first thing you do, you turn it on. If it's this version 2, it will tell you the channel number. The default is AA, like a battery. If you have the white one, you turn it on by default. If you haven't reset it in any other class, by default it will be in the AA channel, and that's what we use. So if somebody else, some other professor told you to change your channel number, you have to wait usually about 10 minutes for this clicker to reset itself, and then you turn it back on, it will come back as the default. We'll test in a second to see if yours register. So that's the first part. The second part, you can also use the iPhone or Android app, otherwise known as iClickerGo. It's a little trickier to register those. It turns out bCourses has a bug that it only accepts 8-digit numbers for iClickers, and the online app has 12. I think. So if you have the app, you need to go and register your clicker on the iClicker website. If you have signed into the Piazza, if you go again on bCourses, there's a link here. Where's my mouse? There it is. So on the B courses page, there's a link to this Piazza external website. It's a educational messaging, conferencing, chat, discussion forum type board, discussion forum. You need to register for it separately. So if you haven't yet, click on it. It will prompt you for your email and a password. You register once, and B courses will remember your registration. From that point on, you can participate in either your section discussions or post questions to other students and to the instructors. So this is a useful place to exchange both ideas, but also get your questions answered. In one of the posts here, I posted last night specific instructions for how to register both these clickers and online, the app versions. What you basically do is you go to, on the bottom here somewhere, the iClicker tab. You click on that. We're still thinking about it. So my page has 2 additional items. Your page will only have 1 item that says iClicker registration. You click on that, and a little field will pop up, and this is where you type your remote ID. Your remote ID on the regular clicker is written in the back. So this little barcode, and then under the barcode, there's an 8-character sequence, typically 2 or 4 letters and 4 or 6 numbers. You type it in here, click register, and if it all goes well, it works. Now, it works at about 90% confidence level, unfortunately, so it worked for me. The way to tell that it worked is that you'll see this little table show up below it with your clicker number and the date you registered it. If it doesn't work, then let your GSI or myself know, and we'll try to track it down. That's about it. So that's the first logistical. So register it. If you have about, actually you have until the end of the semester to register your clickers. We'll do a technology demonstration today. If you use an unregistered clicker, your scores will still be stored in my grade database. And so as long as we associate your clicker number to your name by the end of the semester, your credit will be applied to you. So you have time, but it's better to sort this out sooner rather than later. Okay, the last part that I wanted to bring to your attention is that there's this webcasts link on B courses. It's a link to the webcasts of these proceedings. I'm somewhat ashamed to see myself on YouTube, but if you are not making it to class, you can view these videos online, and it has copies of both the videos and the slides that I'm showing. So in other words, what will show up in this player is both my face and the rest of me, as well as the copies of whatever is projected on the screen, which is usually slides, or some of the zoom-ins into the lecture demonstrations. It's also on YouTube, and it's also on the iTunes UC Berkeley channel. Okay, so without much further ado, let's make a little technological exercise. I need to push some buttons. Okay, so the first thing that we'll try is that we'll actually see if your clickers work. The way we do that is that we have a small poll, and then after today's lecture, we'll upload the results of this poll into Gradebook, and you can see whether your responses are registered correctly, and you can complain to me and our GSIs if they haven't. Before I do that, let me push a few more buttons. There you go. So here's the first poll. Turn on your clickers. If you have a clicker, you have to press A if you have one, you have to press 2 if you don't have one, and C or D if you have some excuses. So I'm starting the poll now. The poll is counting. Let me actually bring this to the screen and this to the screen. Okay. So the question is, do you have a clicker, A, B, C, or D? If you see your clicker number on this, okay, technology is great, isn't it? Okay, this part is useless. We'll answer A, B, C, or D. There are about 100 responses registered so far. This so-called response grid. I'll leave it here. If you see your clicker number appear in this table, that means you're online and everything is working fine. Eventually, the number of responses will exceed the capacity of this piece of software. Usually, we'll wait for about a minute. It just passed now, and I'll close the poll. Okay, everybody pushed buttons? All done? If you don't see it up here, since this grid only has 50 slots or so, and there are 250 of us, that's probably okay. Actually, I agree, it's not a very useful piece of software. Let me stop the poll and show you the results. Oh, okay, so I'm glad to say that only one of you is a rebel and answered E. Everybody else has a clicker. There were a total of 120 pieces of hardware. The rest of you, if you haven't registered yet, will do the same thing on Thursday. Now, a slightly more interesting question. Actually, since this was not so entertaining, to get you into the spirit of actually answering real questions and to kind of stimulate the discussion for the rest of today, let me poll you on a real physics question. Last week, we talked about energy, and we talked about various sources of energy. We talked about the fact that hydrogen generates a relatively large amount of energy per gram. So, and you've read about in the book about the concept of hydrogen economy and how hydrogen can be used as a potential fuel in automobiles or, let's say, in rocket engines. So let's discuss its use as a source of energy for, let's say, the economy or for the cars. There are 4 possible choices here. Hydrogen can be used as a source of energy here on Earth, either because it's very abundant, either because it produces a lot of energy per gram, or because it produces water as the pollution, and therefore it's pollution-free, or because there's a lot of it in the oceans, or no, for various reasons. So let me see what you guys think. Again, we'll do a poll, and starting now. I'll time it for a minute, and then after that we'll discuss. So this is another example of an educational technology. We'll look to see how the responses look and whether any discussion is warranted. So again, A, B, C, or D on your device. All right, okay. So after about a minute, you guys, everybody had a chance to push buttons. About 115 of you, 116 of you have, 117, 18. Last two guys, make up your minds. There were 120 last time. All right, let's stop here and look. So the majority, this is a great example of a democratic process in action. Most of you answered D, that hydrogen is a means of transport energy rather than a source. Some of, however, about equal number, given answer A, B, C, or C, which is the answer is that hydrogen is a source of energy for various reasons. Because it's pollution-free, because it produces a lot of energy, there's a lot of them. So, you know, this is what I would call a wash in some sense. Oh, this is also what happens in the US elections, right? Sort of typical election results are sort of 45 to 55 at best, at least averaged across the country. So, of course, the democratic process usually involves iterations. So, you know, we are nearing midterm elections, right? In about 2 years, there will be presidential election cycle. And the first time the presidential election cycle starts, you guys know the presidential elections start in Iowa. Right? There was this thing called Iowa caucuses, when people in Iowa get together and decide who the presumptive nominee would be, and they don't actually vote. They get together, they discuss, and you know, in each of the caucuses, a candidate emerges. So let's do that too. There's about 50% of you, 47% of you think the answer is D. Some number think the answer is E. And slightly less than 50% think that hydrogen is a source of energy. Now, what I would like you to do for the next minute is to reconstruct the Iowa caucus. Get together, turn around to your neighbor, and if your opinions differ from theirs, try to convince them that you are right. We'll chat for about 2 minutes, and then we'll repoll. I gave you about 2 minutes. So hopefully, you know, those of you who are really convinced were able to convince your neighbors and vice versa. Let's actually see whether you actually, most of you stuck to your convictions or not. So I'll start the poll again, give you another minute to dial in your answers, and we'll see what happens. So register your votes again, A, B, C, or D, or E. Okay, 10 more seconds. If you haven't made up your mind yet, now is the time. All right, let's take a look. Well, I have to say the majority now prevails. That actually is the right answer. So congratulations to those of you who stuck to your guns. The reason for that this is the right answer will be clear in a second. The reason actually is related to the material in today's lecture. What we are going to discuss today is microscopic energy, otherwise known as heat. So let me start right on it. Heat is, in some sense, what we experience is probably the first type of energy we ever experience, actually, even as embryos in your mother's womb, you experience the warmth of her body. You are in touch with that energy source. What you're experiencing as you're experiencing warmth is you're experiencing the microscopic vibrations, microscopic motion of elementary particles that compose your body and all matter around us. So it's easy to experience heat. You can come to a fire and feel its warmth in your fingertips, especially if you come back, say, from the cold, like right now in the Midwest. Come inside, it feels nice and warm. You can feel the energy flowing from that source over the distance. An example of radiation energy transfer, radiation heat transfer. You can make a much more immediate impact if you just rub your palms, rub your hands together. This is a direct example of transfer of mechanical energy. You're producing mechanical microscopic energy of your hands, and then you start feeling warm. You're converting this macroscopic mechanical energy into a small vibrations of elementary particles, atoms, and molecules that compose your body, in this case. And so we describe, we being physicists, describe heat as an example of energy type that is contained in a random motion of atoms and molecules in the body. It really is a manifestation of kinetic energy. Kinetic as an energy associated with motion, except that instead of associating that energy with motion of macroscopic object like this, it's the motion of microscopic particles all around us. We'll have a demonstration of this on Thursday. It takes a while to set up, so we didn't have time. We actually know that this happens. You can visually see microscopic motion of atoms and molecules through a process known as Brownian motion, that is through observing vibrations under the microscope. Or what we'll actually do here is that we'll show you a motion of these microscopic particles when they're illuminated by a laser pulse, laser beam. You can see, if you look under the microscope, vibration of cells. If you ever did a biology lab, you can look at a cell. It's a big blob of stuff, but stuff inside it vibrates. And it vibrates because cell boundaries, molecules are continuously bombarded by molecules of the environment, water inside the cell, or in our case, air molecules bombarding our body, or air molecules bombarding, say, particles of smoke that you can observe visually with your naked eye. Incidentally, it's exactly this fact, the fact that we can explain phenomena of heat and heat transfer, the fact that we can explain phenomena of temperature through the microscopic motion of elementary particles, and in particular we can explain Brownian motion through the elementary motion of microscopic particles is what Albert Einstein received his Nobel Prize for. Incidentally, he didn't receive his Nobel Prize for the theory of relativity. It was for explanation of the Brownian motion, because it has the fundamental, profound effect on how we now understand matter. We understand that matter is composed of tiny elementary constituents, and we call them atoms and molecules. We describe temperatures, therefore, is a measure of how much energy is contained in these small vibrations, in these vibrations of elementary particles. Temperature, by physics definition, is a measure of amount of kinetic energy of the motion of molecules and atoms. The more kinetic energy per atom, the higher the energy, the higher the temperature. And there's, of course, means that there's an absolute zero point of temperature. Now, if you look at the macroscopic object can be at rest, not moving, at which point its kinetic energy is zero, or a macroscopic object can be rolling around, in which case its kinetic energy is not zero. Same thing is true for microscopic atoms and molecules. There is a point where their kinetic energy is lowest. At that point, all atoms and molecules are sitting at rest. This is defined as the absolute zero, the absolute lowest temperature that could be ever possible. There's a third law of thermodynamics that says that reaching that absolute temperature is actually physically impossible. It's a completely improbable configuration. But one can strive to achieve it and get closer and closer and closer to it, to this degree of absolute zero. In fact, you can use refrigerators to cool samples of material down to small temperatures. In fact, I have one of those in a lab in LeConte Hall. We have a device called dilution refrigerator that can achieve some of the lowest temperatures possible. Of about, we nominally operate at the temperatures of about 10 millikelvin, or 1/100th of a degree Kelvin away from absolute zero. In fact, my graduate student made a bet with me, which I lost. I now owe him a bottle of good wine. He claimed, and as part of the bet, he now has to write it in his PhD thesis, that one of our experiments that we are doing in Italy that will operate at a temperature of 10 millikelvin will represent in itself a cubic meter of volume, and this will be the coldest cubic meter in the known universe. That was his statement. The experiment, when we turn it on next year, will be the coldest cubic meter in the known universe, operating at the temperature of about 1/100th of a degree away from absolute zero. And one could actually cool samples to temperatures even lower than that, but not all the way down to the state where all atoms and all molecules stop in their tracks and stand still. That part is the absolute 0 degree Kelvin, is theoretical temperature, absolute lowest possible, but not practically achievable. Of course, when we talk about temperature as humans, we like to use more natural units, and we use degrees C or degrees centigrade if you're in the progressive countries in Europe, and if you're in this strange lands that used to be owned by a queen, then you use Fahrenheit. We'll talk about that. So fundamentally, we can look at the motion of particles. In fact, we can look at, I can sort of simulate this motion. If you were to take each atom, which, atoms usually have the sizes of about an angstrom, about 10 to the minus 10, 1 over 1 with 10 zeros meters. Small number. 1/10,000,000,000 of a meter is the typical size of an atom. If you were to take the atoms and blow them up to, say, an inch diameter, which is roughly this ball, or to a couple of inches in diameter, which is this lead-filled tennis ball. This thing is heavy, it's lead-filled. Then we can simulate the Brownian motion of the molecules and see how the velocity of these objects depends on the mass. So here I have a heavy ball. I have a whole bunch of balls that are obviously lighter. They're made of wood. I can increase the temperature of the sample by shaking the sample around. I give the sample mechanical energy, completely randomly. Can we switch to the screen? Maybe I'll sort of hold it like this. Perhaps you can zoom in. That looks good. So now if I shake this box, now you can see that the light objects typically move a little bit faster. Why is that? Well, if I deposit energy in this box, this energy gets divided roughly equally among all of the constituents. If I deposit the same amount of kinetic energy into the sample, this energy would be distributed equally among all of the constituents. The sample temperature would be equal. But the kinetic energy depends both on the mass of the object and the velocity. Kinetic energy is proportional to the mass times velocity squared. So heavier objects tend to move slower, lighter objects tend to move faster, in such a way that the average kinetic energy per atom is the same for the entire sample. We'll get back to that also. So we understand now these processes of heat transfer. We understand the processes of, we understand the structure of the materials, the structure of matter, as matter composed of microscopic constituents. In fact, the fact that these constituents are tiny, and there are a lot of them in a given volume, in a given macroscopic volume, allows us to actually make quantitative predictions about how heat gets transferred and how the matter behaves. The fact that there's a lot of atoms in a given volume allows us to make averages, to compute averages, allows us to make predictions based on statistical behavior of the samples. This idea that matter consists of tiny elementary objects, atoms, also allows us to make quantitative predictions about both physical and chemical behavior of matter. In terms of the sizes, I said that the typical atomic size is about 10 to the minus 10 meters, of about an angstrom. Atoms, as we now understand, contain a dense, heavy, massive nucleus, positively electrically charged, and we'll get back to that, that contains protons and neutrons, and electrons that orbit around this nucleus. And actually, you often see a picture like this, right? This, atomic energy picture, any atomic energy agency would have a picture of an atom with sort of electrons depicted here on either circular or elliptical orbits. As we'll discuss later in the semester when I talk about quantum physics, this picture is really an illustration, and atoms don't really look like this. The motion of electrons is much more unpredictable, rather random, or rather undeterministic, but we can compute on average probabilities to find an electron in a given place, but we cannot predict for certain where the electrons are. But for illustrative purposes, it's nice to describe electrons and nuclei as forming kind of a planetary system with the nucleus as a dense core, similar to a sun, and the electrons orbiting around it like planets. On a orbit whose size is about 5 orders of magnitude larger than the size of the nucleus itself. Nucleus is about 10 to the minus 15 meters in diameter. a unit known as a femtometer or a Fermi, and the diameter of the typical orbit is about 10 minus 10 meters. And that also defines the typical distances between molecules in a solid or a liquid. In a solid or a liquid, atoms are connected to each other by electromagnetic forces. The electrons on these orbits form bonds, and so the typical distance between the atoms in a solid or liquid substance is also of the same order as the diameter of the atom itself, so that's in the order of an angstrom. And then if you take a single atom and connect another atom to it, you can form a molecule, which again forming a chemical bond. So this idea that matter consists of elementary atoms, and the different atoms can be differentiated from each other by how many electrons an atom has on its orbit, this idea has really emerged in the early 20th century. But it was actually based in the development of chemistry in the late 18th, towards the middle of 19th century. In fact, you know that we can summarize the different behavior of different atoms in this chemical structure called the periodic table. Incidentally, it was first proposed, or rather it was, this, or close to this structure of the periodic table, was proposed by a Russian chemist, Dmitry Mendeleev. In fact, there's a story that the structure like this came to him in a dream. I guess he was working hard, he was working late at night, and at some point he dreamt that there's a periodicity or a structure to the chemical properties of the atoms. We understand this now from the quantum physical principles. We understand now that the fact that the elements in the periodic table, here for example, can be arranged in columns has to do with the fact that for each element in a given column, the number of electrons on an outer electronic orbit that actually participates in chemical reactions is the same. So for example, hydrogen has a single electron on its atomic orbit, but if you go to a heavy element like lithium, lithium would have a single electron that can participate in chemical reactions and two other electrons that are so tightly bound to each other, they're basically inert. Same happens to sodium, calcium, rubidium, cesium, and francium. I think all of those share a similar electronic structure. There's a single electron that participates in chemistry, and a whole bunch of other electrons that form so-called closed shells that are inert. Why electrons form closed shells is explained by quantum physics by the Pauli exclusion principle. Same thing happens for any other column. For example, if you look at the, I should turn my phone off, shouldn't I? That's a good time to turn your phones off too. Elements in the rightmost table, rightmost column, are inert gases: helium, neon, argon, krypton, xenon, etc. They have no electrons on the outer orbital shell that can participate easily in the chemical reactions, and so these elements are chemically stable or inert. They form single atoms. Elements in the first column have one electron. They can give away to form chemical bonds. Elements in the seventh column can accept one electron to form a closed chemical bond, so those are most chemically active. So again, we now understand the structure of the periodic table from the quantum mechanical properties of each atom. Incidentally, you'll notice that there are a lot of elements on the bottom part of the periodic table here that have familiar names. Americium, probably the root of it is America. Berkeleum, kind of obvious. Californium, well, also obvious. the reasons why these elements are sort of named appropriately, californium, berkelium, americium, etc. They were discovered here. They were in fact not just discovered, they were artificially produced. Most of the elements in the bottom part of the table are unstable. In fact, any elements past uranium don't exist in nature and have to be artificially produced, or can be artificially produced in nuclear reactions. We'll discuss nuclear energy, and we'll discuss the fact that you can generate plutonium and neptunium and the process of nuclear reactions, nuclear fission and fusion. But these elements are so unstable, they live for a relatively short time. They have to be produced by fusing relatively heavy nuclei like uranium and thorium with the lighter nuclei to increase the size of the nucleus. They're produced at the Lawrence Berkeley lab at the 80-inch cyclotron just up the road. You can take a tour of the facility if you wish. So yeah, all of these elements are produced artificially here in Berkeley. Of course, what we often say here is that there's still no, and there probably will never be, a Stanfordium. A lot of nuclear chemistry happens here on campus. We now understand atomic theory as we can describe structure of any material, any substance as composed of elementary particles, elementary atoms forming composite objects, molecules, or in more complicated structures, extended structures like solids and liquids, where molecules are tied together by chemical bonds. But this is not a simple theory. In other words, it's actually verified experimental fact that the structure of matter behaves this way. We can verify it by physical evidence, both visually. We can now show you an example of Brownian motion on Thursday, so you can look at it with your own naked eyes. But we can also describe quantitatively, not just qualitatively, but also quantitatively, the processes of energy transfer through conduction, convection, or radiation, all of which are understood as transfers of kinetic energy through either direct contact between the molecules. This is the process of conduction. The process of conduction is the transfer of energy through direct physical contact, where the vibrations of molecules in one body can transfer energy to vibrations of molecules in the other body. This is the process of conduction. Convection is understood as the motion of particles in the Earth's gravitational field as a whole. We'll look at examples of this. And the process of radiation is understood as the process of transfer of energy over long distances without direct contact due to the production of electromagnetic radiation like radio waves because of these vibrations of elementary particles. So we'll discuss more of this in just a little bit. So physics is quantitative science. And so in order for us to describe the behavior of matter quantitatively, we need to define quantitative measure of energy. And so, as I said, we typically, humans measure temperature on a scale that's convenient for humans. And the scale really depends on your perception. It depends on where you grow up, depends on what your everyday experience is. If you grew up in Hawaii, there's really, one degree of temperature that you really need. It's nice outside. Well, maybe 2, right? It's nice outside and the water is warm, right? So there's probably 2 degrees of temperature that you ever need. If you live in the Midwest, then there's, the temperature ranges from, bloody cold, like now, to, very hot in the summer. And so there may be some, range in between, time for a jacket, time for a t-shirt, etc. Of course, these are qualitative descriptions. Quantitatively, we would like to define a scale. So we define temperature as a measure of kinetic energy of molecules. But as it turns out, the actual units of this kinetic energy are not convenient for humans. So first of all, it seems to be an artificially theoretical definition anyway. How would you measure an average kinetic energy of a molecule? Well, you have to find one, kind of look at it, measure its kinetic energy of its motion. Find another one, measure kinetic energy of that one. Find this one, measure its kinetic energy, then add them all up together, divide by the number. In other words, compute the average. Definition of temperature, temperature is the average kinetic energy per molecule. But there are a lot of molecules. So it's this definition, while works extremely well for theoretical physics, is not practical in real life. We, physicists, use it because it makes our calculations easily relatable, but the units are such that it would be inconvenient for everyday life, and so we define temperatures on a more human scale. So on this absolute scale, so we know three scales of temperature. There's an absolute sort of physics temperature scale. And this has to do with this average kinetic energy per molecule. If we define the absolute temperature as the average kinetic energy in some units that can be measured in sort of numbers of from 0 to 100 or few hundred, called this degree Kelvin. This is the temperature scale where the absolute 0 corresponds to molecules standing still and having no motion. And then 300 degree Kelvin would correspond to a typical temperature on Earth. This defines the temperature scale. In these units, human temperature is about 310, and the Earth's average temperature is about 300. Sort of nice, reasonably sizable number. The value of a single degree Kelvin comes from the centigrade or Celsius temperature scale developed by this gentleman, Swedish physicist, chemist, and astronomer Anders Celsius. He actually defined the temperature scale. He wrote a paper about how to calibrate thermometers so that the temperature scale would be repeatable. He wanted to define the temperature also in the convenient metric units from 0 to 100. So he defined the scale of temperature in such a way that in his scale, water would boil at a very specific temperature point. He would define the boiling point of water, the temperature at which water boils at the sea level. I think he was in Gothenburg, not in Stockholm, but say at sea level in Sweden. He defined that scale to be 0 degree C. 0 degree Celsius was the temperature of boiling water. And then he would define the freezing point of water, which is also often experienced in Sweden, as 100 degrees centigrade. This was the original Celsius scale. So in his scale, water would boil at 0, and water would freeze at 100. And so the colder it feels, the higher the temperature. And then, of course, physicists figured out that this was inconvenient. So about a year after his death, the scale was redefined by another Swedish physicist, Carl Linus, I think was his name, to be completely backwards. So now we all understand 0 degree C as the point at which water freezes at sea level, and 100 degree C as the point where water boils. And this defines two data points, 0 and 100, and as you know from geometry, if you have data points, you can always draw a straight line through those. So you can define a linear scale and interpolate or in between. In those temperature units, the human body is about 37 degrees C, normal unless you have running a fever. So 36.6 is what I remember from childhood. And you can convert degrees Kelvin to degrees C by just subtracting the temperature of absolute 0 in these units. The temperature of absolute 0 in Celsius is minus 273 degrees. And so to convert from degrees C to Kelvin, we need to subtract 273. Daniel Fahrenheit was another chemist, and well, actually in the 17th, 18th century, there was really not much distinction between chemist, physicist, drugstore owner, etc. So Fahrenheit was Dutch, Polish, German scientist. He grew up in Poland in the city now known as Gdansk. Poland is near Russia. I experienced that Russia is pretty cold. Siberia is like next door. So it gets colder in the winter there. So Fahrenheit figured out that he needed to define a humanly understandable scale. And so he defined 0 to be the coldest temperature on record. The coldest temperature he could ever remember in his lifetime in the city of Gdansk. He would then reproduce that temperature scale by mixing together ice and ammonia, water, and defining the temperature of 0 to be the temperature the specific mixture would freeze. But historically, the 0 was defined as the coldest temperature in Poland at the time, and then 100 was defined as the human temperature. That's a convenient human scale, right? I mean, why would you ever go colder than the coldest temperature on record? And why do you care about anything higher than human normal temperature? So that defined the typical scale. Of course, to make it more reproducible, humans vary a little bit, and temperature records in Poland vary also as well. So we now define this temperature scale to be tied to the same scale as the degree C by defining 2 points which are much more reproducible, which is the boiling point of water and the freezing point of water at normal pressure. And they're defined to be 32 degrees Fahrenheit and 212 degrees Fahrenheit. And in these units, the human typical temperature is now slightly adjusted to be 98 degrees. Of course, physically, we relate those temperature scales to the actual quantities that matter for the microscopic objects, which is the kinetic energy of the molecules. So the actual temperature on the physics scale, the absolute temperature in Kelvin, is defined as the average kinetic energy. And kinetic energy, if you remember from last week, depends on the mass of the object, its velocity squared, and then there's this pesky factor of 2. So what it means is that the higher the temperature, the more energetic the vibrations of molecules are. So the more energetic the vibrations, the faster the objects move. That's one thing. So the higher the temperature, the faster the molecules move. And the second point is that the larger the mass of the object, the smaller it moves for a given temperature. So if temperature is proportional to this quantity, the more massive the objects are, the slower their speed is, lower their speed is. And vice versa. If you have a molecule at the same temperature as the rest of the environment that's very light, it would move at a given temperature with a much higher velocity. And so that's one of the reasons, going back to the original poll, that we don't consider here on Earth hydrogen as a viable energy source. The reason for this is that while hydrogen is extremely energetic per gram, there's no free hydrogen in the world. It has all escaped. The reason for this is that if you look at the temperatures of 300 degree Kelvin and compute what is the typical velocity of an air molecule is. The velocity, the speed of the air molecule is of the same order, as it turns out, as the speed of sound in gas. And there are reasons for that. The reasons for this is that the sound propagates through vibrations in substance, in matter, in air. And so those vibrations propagate with the same typical velocities as the molecules themselves. So effectively, the molecules transport sound waves in the same way molecules transport energy from one place to another. So the typical speed of sound in air is about 300 meters a second, or as I was telling you last week, 1 mile for every 5 seconds. That's the typical speed of sound, and that's the typical velocity in air. And that's the typical velocity of an air molecule, of oxygen or nitrogen. So here's oxygen. Oxygen molecule has two of those in a single object, so it's sort of, they're tied together like this. So if you look at the periodic table, you can figure out there's this number in the bottom. This number in the bottom for oxygen is 15.999, call it 16, is the atomic mass in units of hydrogen mass. Well, to be exact, it's in units of 1/12 of the carbon, but okay, close enough. So oxygen, single atom of oxygen is 16 times heavier than a single atom of hydrogen. Oxygen molecule has two of these, so it's 32 times heavier than a single atom of hydrogen. Well, hydrogen doesn't usually like to sit in a free form. It typically forms molecules too. So, the kind of most stable form of hydrogen would be a hydrogen molecule that has two of this. So hydrogen 2, it will kind of look like this. And the oxygen will have two molecules of oxygen, oxygen 2. And that's 16 times heavier than a molecule of hydrogen. What it means is that on average, the hydrogen, for the same temperature, hydrogen molecules move. They have the same kinetic energy, but 16 times smaller mass. So the velocity will be 4 times higher. So if the typical velocity of the oxygen molecules is about 500 meters a second, the typical velocity of the hydrogen would be 4 times larger than that, 2,000 meters a second. And in fact, some molecules move faster than that. And so some molecules can move as fast as a rocket ship needs to move in order to leave the Earth's atmosphere. That velocity is known as the first escape velocity or first space velocity, or an escape velocity of 13 kilometers a second. We'll discuss that next week. That if you launch a rocket and it moves with the velocity of 13 kilometers a second, it will leave the Earth. If you're launching something to the moon, you need to have a rocket flying at least that fast. And hydrogen, being so light, can actually be accelerated by these atomic collisions to these velocities. And so over time, hydrogen escapes, just like a rocket ship that's launched fast enough can escape the Earth's gravitational field. So over billions of years of the Earth's existence, all the hydrogen has effectively evaporated from our planet and went elsewhere. It went into interstellar medium, or probably, more likely, it got captured in the gravitational field of more massive bodies that can actually keep it. Sun is much more massive than Earth, so it keeps all of its hydrogen. Jupiter is much more massive than Earth, so it can keep its hydrogen. In some sense, hydrogen is the most abundant element in the universe. About 5% of the universe mass is hydrogen. But it doesn't exist here. It exists there somewhere. It's all in the interstellar medium. So if we were able to mine hydrogen somewhere, it would be a great energy source. It produces 3 times more energy than a gram of gasoline per gram. But there isn't any hydrogen here. So without having an ability to mine hydrogen from interstellar medium, we have to produce hydrogen in its burnable energetic form from whatever resources we have here. And the only resource we have is water. Well, the most abundant resource we have here is water, or we have hydrocarbons, oils, which can be also converted into free hydrogen and some molecules containing carbon. So since no hydrogen exists in the free form and has to be produced, let's say from water, the same amount of energy that is released by burning hydrogen and oxygen producing water will have to be spent to separate hydrogen from oxygen in the first place. And so hydrogen becomes a substance that can be used to store energy. You can produce energy by some other means, by burning coal, for example, or by collecting solar power. Use that energy to separate hydrogen from oxygen in water, store hydrogen somewhere, and then over time slowly use it in a fuel cell or in a rocket ship to use it. But since the same amount of energy is used to produce hydrogen as is released in its consumption, it's no longer a source, but rather a vehicle to transport and to store energy. So your answer for most of you was right. But again, the main reason for this is a combination of thermal motion and the fact that the hydrogen is so light, it just evaporates from our surface. So the other demonstration of that you actually experience in everyday life of this thermal motion and the fact that the thermal motion increases as you increase temperature, you experience this from the phenomenon known as the thermal expansion of materials. Most materials increase in size when you heat them up. Not all of them, most of them. Water is this very specific, strange, kind of fortuitous example that violates this principle. Water behaves kind of oddly, and particularly it behaves very oddly near the freezing point. As it turns out, as you know, ice floats to the surface. What it means is water freezes, it actually increases in volume rather than decreases. That's very fortuitous. Since ice is less dense than water, it tends to be on the surface of rivers and lakes, and so it covers the top of the lakes, insulating them from the colder temperatures, and that actually allows life to persist, allows the lakes to stay relatively liquid throughout the winter with only a layer of ice on the surface, and so allows complex life to persist throughout the cold winters. That's very good for evolution. Most other substances, however, typically expand as we increase their temperature. And they expand by the amounts that can be measured in sort of parts per million per degree C. The reason for this is actually pretty obvious. Let me take the heavy ball out. If I start with a relatively low energetic system, so here's the system with zero at the zero kinetic energy, so effectively near the absolute zero, it can occupy the smallest amount of space possible. Right? I can pack the substance relatively tightly. If I increase the energy, the stuff tends to spread out. And so the volume occupied by the substance as I increase this energy grows. And if I increase the energy more and more, it spreads out further. James will hate me. He will have to collect all these balls. So this is the basic explanation for why materials expand as we heat them up. And the amount, of course, depends on the chemical and physical structure of the medium. Let's switch back to the screen. So if you have a solid object, solids or liquids like metals, glass, expand by the amounts that are typically on the order of 20 parts per million per degree C. These are relatively small amounts. So, you take a piece of metal like this. Here I have actually a stick that has two metals on two sides of it. Think one is called invar. Invar stands for invariant, I think. It's a alloy of, I think there's copper in it, and there's some iron, I believe, in it, and some admixture that make the coefficient of thermal expansion very small. It basically makes one side of this bimetallic strip to effectively remain unchanged as I increase the temperature. Another side is covered with brass, and the brass has the coefficient of thermal expansion of about 2 times 10 minus 5. So these are small amounts. So in other words, the size of the object, so what does it mean? That if the size of the object changes by 20 parts per million, or 0.002% for every degree C. That seems like a small amount, but this small amount can still be observable. So in particular, you can see it if you have materials that expand differently. You can see the difference in the expansion macroscopically. So here I'm heating up this bimetallic strip, and the stick that used to be straight when I started the process starts to curve when I heat it up. So you can see physically observable features. You see that the left side expands less than the right side expands more. It tends to increase its length and therefore curves the stick to the left, to the side which has the smallest coefficient of thermal expansion. So even though these numbers seem small, 0.002% per every degree, multiplied by large distances can produce observable, quantitatively observable effects. So again, if I want to compute, let's say, what is the change in the length of an object is? Change in the length of the object would be this coefficient of thermal expansion. It's called alpha. So this is this 2 times 10 to the minus 5 per degree C. And I need to multiply it by the length of the object and multiply it by, so let's say this might be in meters, and I multiply it by change in temperature in degree C. So if you start with an object that's small, say you start with an object that's a meter long, like this, 3 feet. And you warm it up by degree C, the meter will change to a meter plus 0.001% of a meter. What is that? That's less than a millimeter. That's about 10 microns. Of course, if you start with an object that's 10 kilometers long, and you heat it up by a degree C, and say you started with something that's a kilometer. Kilometer is 10 to the 3 meters. And let's warm it up by 10 degrees C. And multiply by a coefficient that's 2 times 10 to minus 5. What is the change in length? 10 to minus 5 times 10 to the 3 is 10 to minus 2 times another factor of 10 and 10 to minus 1. It becomes 0.2 meters. So if you start with an object that's 10 kilometers long, say Bay Bridge, is what, 7 miles? 10 kilometers. Bay Bridge expands over, between the night and the day. It's about 15 degrees C, it's going to be about 15 degrees C today at high noon. It's probably close to about 5 degrees C at night. So Bay Bridge changes its temperature by about 10 degrees centigrade between night and day today. And that means its length will change by about 20 centimeters. That's like this big. So if you integrate the small changes over large distances, you can produce macroscopic effects. And these macroscopic effects, of course, have to be taken into account when you design large buildings. Bay Bridge, obviously, if Bay Bridge was built solid, what do you think would happen with it? It will change its shape like the stick. And so at night, Bay Bridge could be straight, and during the day, it may look like a camel's hump. Would be somewhat inconvenient to drive on it. And probably over time, these repeated stresses, repeated expansion, contraction, repeated forces would break it. So engineers know this for a fact. So engineers build into designs of most large buildings allowances for this thermal expansion. So every bridge has thermal expansion joints in it to allow for the differential contraction and expansion as a function of temperature. Every tall building is designed with that goal in mind. Every levee that has to hold floods also is designed with that goal in mind. And as the book discusses, one of the places where New Orleans levees failed was in the thermal joints that are the weakest points in the whole structure. You can, of course, design materials that have low coefficients of thermal expansion, but materials that are nominally used for construction, like concrete and steel, expand actually rather significantly. Gases, of course, expand even more. So the reason for this is that the gases gas is a collection of relatively loosely related objects. In fact, to first order, molecules in air don't interact with each other at all. They kind of bump into each other every once in a while, sort of like you bumping into your neighbor in the hallway, but really there's not a lot of interaction. And so as you heat the gas up, nothing holds the molecules together, and they just tend to fly apart. And so gases expand significantly more per unit of temperature than the solids and liquids. So these expansions can be very, very significant. Here's an demonstration of that. Well, of course, the flip side of the thermal expansion is that if you cool a sample, it will contract. If you warm the sample back up, it expands. So my favorite demonstration of this process involves liquid nitrogen. So as we'll discuss in just a second, there are three forms of matter that we know, obviously: solids, liquids, and gases. Ice is solid water, vapor is a gaseous water, and we know normally water is a liquid. We can take nitrogen that exists in the atmosphere in its gaseous form and cool it down. Cool it down to the temperature of about 70 degrees Kelvin, or about minus 200 degrees centigrade or so, and it forms a liquid. This is this liquid. Of course, we can keep it in the thermos. We'll discuss the convection and conduction properties of materials on Thursday. And so we'll discuss why a thermos has evacuated walls in between. Has a vacuum in between the two walls, and why it keeps heat out. Liquid nitrogen is a very convenient medium to cool stuff. Well, we can cool liquid nitrogen first, and then use it to cool other substances, in particular gases. So if I pour some amount of liquid nitrogen here in this bowl, of course it starts boiling right away, starts to evaporate, but I have some time to use it as a cooling agent for this rubber balloon that contains air. And as you see, as the balloon cools down, it shrinks. Shrinks by a very macroscopically significant amount. You can see it. And eventually it will shrink to its almost uninflated size. If I then let it sit, it will expand some more. So reducing the temperature of the balloon can shrink it significantly in size by sort of factors of 2. Increasing its temperature will increase its size. So gases expand quite a lot when they're heated. And of course, the gases expand even more when they change phase. So as I said, there are 3 phases of matter that we know. You can talk about plasma, but there are 3 standard phases of matter that we deal with in everyday life: gases, liquids, and solids. And the main thing that you need to remember about the gas is that the gas is dilute. Gas is an example of a substance where the chemical bonds or physical bonds between molecules are very weak. And so the molecules are allowed to roam completely free, and so therefore occupy as much volume as you let it. So typically the densities in the gas are 100,000 times larger than the typical density in a liquid or a solid. And so if you convert a liquid or a solid substance into a gas, the volume increases dramatically. And that increase in volume can be used to produce physical work. It can be used to convert this thermal energy into a kinetic energy, into motion. Here's the best example possible. Again, I'll take my favorite cryogenic liquid, liquid nitrogen. If I pour it into the bowl and close it with a cork, what do you think will happen? What happens is going to be similar to what happens to a champagne bottle when you let it loose, to champagne cork. It doesn't want to stay in. There you go. Right? The expansion of the gas as it boils, the factor of 1,000 increase in the volume, can be used to produce macroscopic motion, macroscopic kinetic energy. So this is an example of conversion of thermal energy from the random motion of the particles that produces boiling, increase in the volume of the gas, into a mechanical motion. Of course, opposite can be true as well. In other words, if the substance warms up, it expands. It probably will require you to think for about 5 seconds to realize that if you let a gas expand dramatically without giving it energy, it will cool down. The whole process of expansion requires energy. So if you take a certain volume of the substance and allow it to expand quickly, its temperature decreases. This is the principle used in the operation of the fire extinguishers. The fire extinguisher has a carbon dioxide gas, actually liquefied under pressure. And so if it has a relatively low volume. If I let it expand by a factor of 1,000, its temperature decreases, and decreases so much that the normally gaseous carbon dioxide state converts into liquids or solids. Okay, it has a safety. They have to pull. Oh, actually, I don't. Right? So expanding the gas volume by a factor of 1,000 reduces the temperature and can reduce it so much that the carbon dioxide gas converts into dry ice. And of course, dry ice is sort of useful for fighting fires. Prevents oxygen from getting to a sample and also cools it down. And the consequence is production of snow, which is actually nice on a hot day. Anyway, we'll use this fact, the fact that this expansion produces a large force, in addition to reduces the temperature next week. I'll show how to use fire extinguishers as a jet engine. So I'll see you guys on Thursday.